Welcome back to the engineering mechanics class that you have been waiting for your entire life, so you can learn more about internal forces. And we already started talking about internal force diagrams, and of course today we will continue that talk. But last class we talked about concentrated forces and how they act on the internal force diagrams. So today I want to talk with you about distributed forces. And so the first thing I want to do is I want to analyze or think about what effect evenly distributed forces have on the internal force diagrams before we then take it up a notch and think about the effect that we have when we deal with non-evenly distributed forces or arbitrary distributed forces. And again, we want to find out how they impact the internal force diagrams. And at the very end of this lecture, we should be able, therefore, to describe internal forces at any point, and any point in this case means at finite increments along a beam axis before we will take it to the next level in our next class and talk about how we can describe really the internal forces at every infinitesimally small location along the beam. But today we want to still keep it finite and look at very particular points along the beam by using the effects that we will analyze. So let's go ahead and get started and think about the effect that self-weight or an evenly distributed force has on the internal force diagram. And to do that, let's of course first draw a cutout section of a beam. So let's say this is my rigid body here, which therefore deserves a dashed line, and it is loaded with an evenly distributed force. So that would look something like this. And this beam is some element cut out somewhere out of a beam. So I cut this out here and I cut this out here. And of course, in reality, I release internal forces if I do that. And the internal forces that we would release would look something like this. You remember this from your study card. I have the shear forces on both sides because I cut on both sides. And I also would have normal forces on both sides, which I am not trying to calculate right now, but I want to think about how they conceptually would look like. And to conceptualize that, I want to introduce a length here of that member that could be really anything. It could be as short as dx, it could be 5 meters or 5 feet or whatever, but I just make this x and maybe meter long. So the length right now is just symbolized by x. And now I want to go ahead and draw the diagrams below this beam that I can conceptually understand how the distributed force impacts the shear force diagram that I will draw right here. And then later on, I will draw the moment diagram right below it. And what we have to understand here to extrapolate our understanding from these pictures later on is that, of course, this is cut away as well. And so these beams are just x long as well. And what that means is that I do not know exactly what value I will have at this location, right? So I will just think about what impact this force will have. And keep in mind, we call this force usually W, and usually that's given in force per distance. And so we need to think about what that means. And remember something that we discovered last class, that we actually have a relationship between the different cases. And one of the first ones that we talked about was, well, the first one we talked about was actually that the shear force is really equal to the derivative of the moment. But another one that we also introduced is that the force case or the load case, let's call that minus W, is equal to dV dx. And we can now think about what that means in the context of the evenly distributed force here and how that impacts the internal force diagram. So we have a force that's actually pointing downwards. So because it's pointing downwards, that's where the negative here is coming from. And we are now going down with a certain force per a certain distance. So for example, let's pretend that W would be equal to 10 kilonewton per meter. And if I would have that unit, what would that mean? That would mean that my force pushes down with an additional 10 kilonewton for every meter I move from left to right in this case. So if X was 1 meter, I would have a total of 10 kilonewton on the system. If X was 2 meters, I have 20 kilonewton because I multiply it by 2, and so on and so forth. And so you can already see from here and actually from here, because this is a constant, that here for the shear force diagram, I must have a slope, right? So what I really would end up with would be a sloped line or a linear function that in this case would slope from the top left to the bottom right. And I purposely am not drawing it symmetrically in this case because remember that this location here could just be x1 and this could be x2, and therefore we could have any value as long as it slopes down in this direction, because we have actually an addition of, for example, 10 kilonewton per meter downwards as my x increases. And remember that this applies, or what we did last time is that every time we had a concentrated force, the internal force diagram for the shear force really jumped down. And so that is an important concept you need to understand, that the jump is actually reflected here as well, except the jump is continuous really, right? So for every meter that we're moving from left to right, or for every increment I should really say, we're actually jumping down. Except we're not going to the right and then jump down, go to the right and then jump down, go to the right and then jump down. We're going down all the time with W as we move from left to right. But you want to think about this as, for example, that every meter you go to the right, you jump by whatever value. So in our example here, 10 kilonewton. So if I were to draw this conceptually speaking, then I would have a jump here, or a step that would jump down by 10 for every 1 meter. And I could do that again for the adjacent portion here, and so on and so forth. So it would always be the same. But of course we're trying to do this conceptually here right now, so I'm not hung up on the values. I don't want to worry about the values. I want to worry about the fact that here I have a constant function which is pushing down, and therefore, because my reference fiber is on the bottom, I have a slope that slopes from top left to bottom right. And this is true for the shear force at all times if you have a distributed force. Of course, your starting value and your end value may change a little bit, but it is always true. And therefore, we actually always end up with a linear function. So let me make space here and clarify that we have a linear function. And of course, this function will describe the shear force. So we will call this the shear force of X. And to describe that, let me say that I have a value right here as a starting point, which of course is arbitrary in this case. But remember that I started at x1, so I call this value V of x1 really, right? So this is the shear force value at x1. And what I end up with then for my linear function, because I'm starting here and I'm going down, 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 down with a linear fashion, I will end up with V of x1 as the starting value, in this case, minus W times X. And let's talk about this real quick. The V is, of course, in, let's say, kilonewton. or in force units really. And then I have the W, which is in kilonewton per meter, for example. And my X is really in meters. And so therefore that works out, right? So the W is really the function that describes, in this case, the constant function of the distributed force. So that's where I come to this equation here, which works out to be kilonewton. And that's important, of course, for us to end up with kilonewton values everywhere along this line, because our goal is to describe what is the value here, what is the value here, what is the value here, and so on. So everywhere along X. And those X values everywhere along this line will actually help us to understand how to interpret the moment function, which of course will become a function too now, because we see this relationship here. So what we want to do is we want to end up with the moment diagram here on the bottom that of course is going hand in hand with this and this function here. And since we already see this relationship here, we can of course also, at least conceptually, integrate. You can do it mathematically too, but sometimes there are some traps you will fall into. I talked about that in the last lecture, but remember that you can integrate from the shear force to the moment diagram. And what does that really mean? The integration is really reflected as the inverse of what you see here, in a sense. And so I want to talk about the meaning of this function here, or the derivative. So what is the derivative really? The derivative is the slope, right? And I know that you learned that in mathematics before, but I have learned in the classroom that students sometimes have a hard time to really interpret this when it comes to physical meaning. For example, the relationship between the shear force and the moment diagram. So I want to be very explicit about that. So let me repeat that. This graph is the derivative of the moment. And what does that mean? That means that every value along this graph really describes the slope of the moment function. And so we can use that to our advantage and really apply our understanding of the shear force function. For example, I can say that I have a very large value here, at least compared to all other values along that graph. In fact, it's probably larger than this value here, so I call that a small positive value. And then here I have a small negative value, and here I have a large negative value, or the smallest value of all of them here. And of course, the one thing I never need to explain to my students is that here I have a zero value. So here V of X is really equal to 0, or the shear force at that location is equal to 0. And therefore, everybody understands that when you go to the primitive, or the parent function as I call it sometimes, I have a local maximum or minimum here. And that is something we can often agree on in the classroom. What we don't agree on is really what function comes from the integration from here to here. Of course, you would think right now, this is a linear function. Therefore, of course, I have to go up by 1x, and therefore this will become a quadratic function. And that is definitely true. And of course, that is also something I can get across easily. What I don't get across easily is in which direction the quadratic function will be pointing, if you want to call it that way. So for example, it could be belly up, as my students call it in the classroom. It could be belly down. It could also be like this. But in reality, it cannot be anything else than a very specific function that I want to develop with you right now. And that relates to these values that I drew here. So remember that this is the derivative of the moment, and therefore this value here describes the slope at this location. So let me actually call this here, for example, XA, and then here I call this XB, and then XC and XD. And what you need to understand is that this value here describes the slope of the moment function at XA. This value describes the slope of the moment function at XB, and so on and so forth. So this is a smaller value, and this is an even smaller value. And of course, somehow we all understand that for the 0. So I can actually go ahead and draw the moment function, and I can draw the tangent. So let's pretend here I have a tangent that is 0. But now let's look at xa and xb. At xa, I have a very steep slope, right? It's a larger value. So let's just pretend that's somewhere there, the tangent. And then at xb, I have a smaller slope, and that would look like this. And at xc, I have a negative slope, right? That's important to understand. And that negative slope is somewhere here. And then at xd, I have a larger negative slope, or a smaller slope, if you want to call it that way. And so that would look like this. And so let's pretend that my tangent is right here, and here, and here, and here, and last but not least here. And now I can connect those points and really draw my parabolic function that could not take on any other shape than this. And first of all, we understand that it's positive, and that is now our complete moment function. And of course, we understand that we cut it somewhere randomly, so we actually also end up with a value of m of x1 here, and then here m of x2. But again, I'm not worrying about those values. What I worry about is that here I have m max, and that I actually related this point to this slope, and this point to this slope. And please note that this is positive here, and positive means that this is a positive slope. Remember what a positive slope is: from bottom left to top right in a 2D coordinate system in the first quadrant, whereas a negative slope in the first quadrant would be from top left to bottom right. And so we related each of these shear force values to the slope of the moment function, because we know this here, and therefore we can unmistakably draw the parabolic function and the shape of this moment diagram. And let's talk about the unmistakably part here for a second. So students sometimes tend to think, this is positive here, therefore my moment diagram must be positive. But you can already tell from this diagram that this is not the right logic, because here it's negative and my moment diagram is not negative here. So what does the positive and the negative mean? The positive and the negative relates to the slope only, and slope again has something to do with in which direction the diagonal line is sloping, right? So either up from left to right or down from left to right. And you can see that everywhere here where the shear force is negative, the slope is going from left to right downwards, whereas here where the shear force is positive, the slope anywhere along this function is moving from left bottom to top right until we hit 0 here, and that's where we then turn around. And that's exactly shown here. So mathematically, students always know this, but really turning this into a shear force to moment relation is sometimes challenging. However, I hope this will help you to clarify this and to understand that this will always work, because we start with a constant function. In fact, let's understand here that this is always a constant. And then, therefore, we end up with first a linear shear function, but then we have a parabolic function for the moment. And that is always true as long as you have a constant or evenly distributed force. So under self-weight, which is really represented by this, under self-weight you will always end up with a linear shear force function and a parabolic moment function. And don't get me wrong, of course you can have distributed forces that actually push in the other direction, then this whole thing would flip around. So for example, here we would have negative values and here we would have positive values. And then also the beam would not be smiling, right? Remember, this beam is actually smiling, therefore everything has to be positive. But if you push up with a distributed force, then the beam would be frowning and therefore everything would have to be negative. But you will learn this through application. In fact, we will actually apply this today We will not calculate the values everywhere along the line, and we will not set up functions really. That is our goal in our next lecture. But to really understand how these diagrams come about, we really needed to talk about the relation here between the distributed force and the shear force, and the shear force and the moment, all for effectively self-weight or evenly distributed forces. So the next thing for us to do now is to analyze what happens if we make this a little bit more complicated, and what happens if we don't have self-weight or evenly distributed forces anymore. What happens if we have non-evenly distributed forces? So let's move on and take a look at that concept. What happens when the load case is not as nice and evenly distributed as before? And to do that, I want to bring in my same piece of the beam, which of course is a rigid beam and is also cut at an arbitrary distance. But in this case, I will now have the next more difficult load case, which would be a sloped line. So think of this here as WA, let's say, and then this here is the value WB, just indicating that we have different values on both sides, but in between they are actually linearly connected. So I have a linear slope here. And of course it comes out of a random space, out of some beam, so I cut it, and every time I cut it, I of course have to bring in my internal forces, just so that you don't clinch when you look at these pictures. But at the end, we are not worrying about these right now. However, I want to include them for completeness reasons, so that we get used to this picture. And now I can apply my lengths here. So I want to let you know that this distance is once again just a random distance in the beam. So it's x in meters, for example. And we now have a linear sloped load case on there. So when could this be the case, by the way? So think of this as like a brick wall that increases from the left to the right. Or for example, this could be just the left side of a house where the roof slopes up, right? So you could have different load cases that actually represent a linearly sloped distribution. But my goal now is to think about what happens if I want to apply that load case to my shear force diagram. And to draw the shear force diagram, I start with my rigid body and I start calling this the shear force. And the thing that I remember, right, is that here I now have a linear load case. And I also remember that minus W is equal to dV dx. And thanks to that formula, I can now extrapolate my knowledge from the previous section and understand that I can also take the load case and integrate to arrive at the shear force function. So now it becomes a little bit tricky because we have the minus here, but there's nothing that we can not solve. We can, however, use the similar logic and move from this sloped line to the shear force function here. And to do that, let's first indicate again that this is a cut system and that now I have to end up with a parabolic function, right? Because again, here it's linear, the load case is linear, and I now need to end up with a parabolic function. And that parabolic function needs to reflect this slope. But now be very careful, because this slope here once again describes just the value of the slope of the shear force. So I say that again. This value here describes the slope of the shear force function at that location. To clarify that better, let's bring in our 3 or 4 distances again. So let's say here I have XA, then here I have XB, I have XC and XD. And maybe to better communicate that, let's change this up here to WD now, so that we understand that that relates to each other. But what I can do now is I can say that this value here relates to the slope of the shear force function. And so I have a small value there, and yeah, don't be fooled, it looks like it's positive, right, because we are above the dashed line, but keep this negative in mind. So sometimes when people see this negative, they just want to draw a negative function here, but it's the slope that is negative. So what does that mean? I have a negative slope that is not very large at XA. So I have something that is maybe like this. And then at XB, it's a little bit larger. So I'm actually drawing it a little bit steeper. And then at XC, it's very steep. So let's pretend that's right here. And then at XD, it's very, very steep. And so I actually now have my tangents, which let's say apply in this location here. And therefore I can now go ahead and draw my parabolic function. Hopefully I can do a good job here by hand to draw a parabolic function that goes through these tangents. And I think that's okay, at least it gets the point across. So hopefully that will help you to understand that we're really looking at this distance here and this distance and this distance as well as this distance, and we're looking at these values particularly to really describe the slope at a particular location. So this slope here, the one that is tangent to the function, is really described by the numerical value at this location XA. So the slope is defined, slope of shear function described by the value of the load case. At particular location. So at location. And that is exactly why this slope here, for example, is steeper than the slope that I drew here. Because we have a smaller value here and then a larger value here, and here a very large value. And again, be careful, because the minus here tells you that although you have a positive value here along these red axes, you will end up with a negative slope. So we now are ready to actually indicate our diagram and state that all of this here is really positive shear force, whereas this down here is a negative shear force. And this is just a symbolic representation, because we don't know what's going on here on the left, we don't know what's going on here on the right. We're just stating that due to the linear slope here, we would have a parabolic function that slopes, in this case, downward. And of course, we randomly let it go through 0 here. This could be different depending on what happens here and here. And so you hopefully understand that this entire shape could move all the way down, so that everything is a negative shear force. It could be completely up, so that everything is in positive shear force, or we can move this anywhere along this line, depending again on what happens here and here. However, when we move on to the moment now, this of course has a very important impact on the moment diagram, because you know that your moment is really the integration of the shear force. So let's highlight that one more time. So we integrate. And if we integrate, we know that at this location we must have a local maximum or minimum. So when we integrate the shear force function, then we go through 0 right here, and therefore we must have a maximum in our moment diagram. So let's go ahead and draw the free body diagram, or a cutout of that, and let's include that we now have to consider a local maximum or minimum. In this case, I'm very certain that it's a maximum for the very same reason that I used before. So it has to be a positive value here because we have a force that pushes down on the beam, and therefore it makes the beam smile, which means that the reference fiber is in tension and the top of the beam is in compression. And therefore we must have a positive value here without a doubt, because there's no way that the beam could be frowning anywhere from here to here. So that leads us to the next conclusion, that here, everywhere along the part that we see here, we must have a positive moment. So I can already state that everything here must be positive without a doubt, because our reference fiber is in tension through and through. Now you may think, if I integrate a parabolic function, I of course end up with a cubic function, right? So you will find a cubic function here, and you might think, how do I now get to this cubic function if everything is positive? Don't my cubic functions usually look like this? So I'm going to erase this in a second because it's a very particular one, but a particular function, but you probably think of this cubic function right now that looks a little bit like this. And that is a cubic function, but this is a very specific cubic function, right? It's the cubic function that passes through 0 right here, but really what a cubic function tells you is that you have a possibility of 3 crossing with the x-axis. And therefore, you do not show this part of a function, or you could just show a small section of that, and you don't have to have this inflection point here. You can actually have a cubic function that is really represented by the values of the derivative. So for example, here at xa I have a value, at xb I have a value, and then at xc I have a value of 0, and then at xd I really have a value that is negative. And so that has to be represented now. And remember what we just learned or relearned or rediscussed, that the value here along those lines describes the slope of this function. So what does this mean? Here now I have a, be careful, positive value, right? It looks weird because we're going down here, but it's a positive value. So therefore everything to the left of this line has to be positively sloped. So what does that mean? That means I have a large positive slope here initially. So I have a large positive slope, let's say here. And then I have a little bit less of a slope. So that would be right here. And then I have a 0 slope. And then I'm going in the negative direction. And that is exactly the same logic that we used before. So now I can mark those tangent points. And I can go ahead and draw my cubic function, which may not look very different from a parabolic function, but trust me, I'm doing my best here to draw a parabolic function that is reflected now by those slopes. And let me indicate those slopes for you with the thick lines that I used before. So just so we understand that this here, of course, is one of those slopes. And then here I have the maximum where my tangent is 0. So now I think we can agree that the graph here on the right is very a special case of a cubic function, and it does not always apply to our diagrams, because what we see here is a very specific case of a cubic function, and the way we actually get the slopes of that function is really through the shear force function. And therefore we now completed the cubic moment distribution for a non-evenly distributed load case. And this is a very simple load case. Before I talk more about that, let's just complete the diagram here, and let's agree that all of that is now in positive bending because the entire beam is smiling, as we discussed before. Now again, this is a very simple case of a non-evenly distributed force because we can describe it by a simple linear slope. So it's a linear function which then ends up in a shear force that is parabolic and a cubic moment. You may imagine that we can also make this more random, or we could, for example, make this a parabolic function that exists in real life. You can also make it a sine function or a cosine function, but the concept would remain the same. You would just integrate to get the shear force, and then you would, of course, pay attention to the negative here, but then you integrate further and get the moment. Now you may ask yourself, why am I emphasizing this so much, and why are we doing this here with a lot of emphasis in this class? And the reason is you will actually live off this as an engineer later on. And if you think this is challenging, please understand that you actually will take this further in the future. You can actually further integrate even the moment function to find more valuable information about this beam here. So you can further integrate and find, for example, the slope that this smiling beam will produce and the deflection. Let me visualize that for you, and let me make explicitly clear that this is actually not part of the lecture, which is why I'm going to put it below the page here. But I need you to know this so that you know A, what you're in for when you go through your engineering career, and so that you understand why you want to pay attention to this topic so that you can later on apply the same knowledge. So when this beam here starts to smile, it actually produces a curvature of the smile, right? It can smile a lot or only a little bit. And so it turns out that if you actually integrate the moment, you can define the curvature. The way that engineers do that is really by this angle here. So let's call that theta, the angle to the horizontal direction. And so if you integrate your moment, you actually find the angle, and you can do that at every location, right? Just like we did it for every part along the axis for the moment and for the shear force. So you can find the angle that the beam has at a certain location. Now you may not fully agree with me that that is important to know, but you probably agree with me that the next thing is important to know, and that is when the beam deflects, it actually has a vertical displacement. So if I want to draw the smile of the beam, it probably would look something like this, let's say. So this is how much it would smile. And again, the angle here is really theta. So I'm going to mark this one more time for your reference. But what we really want is to know how much this deflects in this direction, right? So this we call delta. And that is something we can find by integrating the smile angle, or what I call theta here. And you can already see that where theta turns to 0, right? So if I would draw the tangent of that smile that is actually 0, of course I will end up with the maximum deflection, because where the angle is 0, and I integrate that 0 slope, I will find a maximum for the deflection, because I can really take this all the way down to find even my deflection. And why is that important? Because engineers often build critical structures where the deflection needs to be limited. For example, if you have ever noticed that the shopping malls have huge shopping windows, then you also have seen that there is a very long span length, and of course the longer the span is from left to right, the higher the deflection can be. So engineers need to ensure that this deflection does not get too large, so that the beam would actually push on the glass beneath it. So the glass really needs some breathing room because it's so brittle, and engineers have to make sure that the deflection value stays within certain limits and keeps some room between the glass and the beam. Likewise, every bridge and every building that you probably currently sitting in is limited in their deflection. The ceiling above you right now is limited so that the public feels safe in those structures and does not think, oh, this is bending or smiling too much. So the deflection for those structures needs to be limited. But let me make that one more time explicitly clear. Everything you see here below is really not part of the lecture. It was a good fit here to talk about it because we started to integrate from the load case to the shear force to the moment, and the next logical consequence would be to take it to these two levels. But that is something you will encounter in your future and in your engineering career. For now, I believe we can conclude this page and we understand how these functions relate to each other. We first started talking about self-weight or evenly distributed forces, and we saw that the shear force became linear and the moment became parabolic. Then we took it up a notch and talked about non-evenly distributed forces and the simplest case, which is a linear slope, so that we learned that we have a parabolic function that is produced for the shear force and a cubic function that is produced for the moment. And then in the future, you will take it to even further levels. But I believe this is everything we need to know now, so we can actually conclude this and summarize this on the following page. All right, so you see a wonderful and beautiful table here, which I will use to give you some tools that can help you to identify quickly what shear force function you will encounter and what moment function you will encounter depending on the load case. And the load cases that we discussed here are the concentrated force, the concentrated moments, the evenly distributed load, the very simple non-evenly distributed load case, which is linear. And then, of course, we're also going to look at no loads. And the way I want to do that is up here, I will put in what effect these will have in writing, and then I give you a representative diagram for that effect so that you have that as your reference. And we're going to do the same thing down here for the moment. And you can see that I already included the load cases as a symbolic representation. I invite you to do that too, so that we then can move on and start with the actual representation. Let's start with the concentrated force because that's where we started our lecture as well. Let's remember that the shear force diagram actually encounters a jump or a drop in the diagram. What do I mean by that? I mean that you, of course, have a rigid body, and that one has a jump right under the force at the same amount that the force actually produces. So the vertical component of that force actually leads to that jump or drop. And then this portion here is positive, and this portion here is negative. This, of course, could be the other way around. If your force, for example, is pushing up, then the jump would go from negative to positive. And likewise, this could also go from negative to more negative, right? So we understand that this just represents this jump here that we are trying to get across here, that this force causes a particular jump. Let me make clear that this is still the cutoff. And now we are ready to move on to the moment below, for which we've seen that we have an inflection point. Inflection point. Because we switch slopes from positive to negative. Sometimes it's from positive to lesser positive or from positive to more positive. It really doesn't matter. What ends up to be the case at all times is that you end up with an inflection point. And so if I want to symbolize that for this case here, let's just say that I have something that goes up here on the left side and then goes down on the right side. And of course, this could go in any direction. So I'm just going to symbolize it as such. And the important thing is to understand that this is a positive slope and this is a negative slope. And now I need to indicate that I cut this one as well. And that completes this diagram. Technically, we usually add these as well here, but it's not the point to say that we have a positive area and a negative area here. But it's important to state that we have a positive slope and a negative slope because of the relationship to the shear force. Now let's look at the next case, which the one that we discussed next in the class was really the evenly distributed load. And for that one, what we see in the shear force diagram is that we have a linear increase or decrease. And the way that looks like is the beam with the dashed fiber underneath now has a linear function acting somewhere randomly along the beam. And again, this is positive and then this is negative, but it could also be all negative and all positive. it doesn't really matter. What matters is that this slopes down from left to right. So this point here could also be beneath the beam, for example. Or this point, like all other ones, could be above the beam. It doesn't really matter. But generally, we understand that we have a linear behavior here. And what did we learn about that and how it relates to the moment? That we now have a parabolic moment function. So it's x squared, if you will, and the way I would draw this, of course, would be with a maximum under the shear force where it goes through 0. So maybe I should include that here so that there's a relationship between the two. And I could do the same right over here. Actually, let me indicate that this here is an inflection point. That's the most important part about it, but we are working on the evenly distributed load right now. So what we found is that we have a maximum somewhere along this line. And because we have positive values here and negative values here, we have a positive slope on this side and a negative slope on that side. So let's indicate that. And let's state that on the left side, we must have a positive slope, whereas on the right side we must have a negative slope. And so this is positive slope, which then of course is parabolic. And I'm doing my best here to draw a parabolic function by hand. This is negative slope. And that is that. Of course, in reality, there is an area underneath it, but that's not the point of this diagram here. But just so that it looks complete, let's add that as well. All right, then the next one we talked about was the non-evenly distributed load case, where we actually end up with a parabolic function for the shear force, right? So here we add parabolic. And of course, that means that here we look at cubic. We will talk about that in a second. Let's first complete the shear force diagram, which we said has to have, actually in this case, a slope of 0 here. And then it decreases and decreases and decreases and decreases more, even more, if you will, and even more. So it gets steeper and steeper. And so I can now connect these tangents. And in this case here we would look at positive and at negative. But again, the point is not to have positive and negative areas here under the graphs. That is not the point of this. The point is to understand that this entire system here, from here to here, could shift up and down completely. And you need to understand that it would then bend down with this shape here. Actually, I believe we can do much better than this, so let me try to make it prettier here so that it looks more like the function we would expect. All right, and of course now there's a relationship to the bending moment that is the same as always, which is where it's 0, we need to find a maximum, and we need to have a cubic function. So let's draw that cubic function, at least conceptually. And let's state that we actually have a positive maximum here, and we have a increase, another increase, and a lesser increase right there at 0, and then goes down. And so then I have a cubic function which looks something like this. And again, this happens to be positive, but the important thing is to understand that this here is positive slope and negative slope. All right, so those ones we have discussed in length as well, but we also touched upon some other ones, which is the one for the concentrated moments. So let's do that one first. So let's talk about the concentrated moments. What happens for the shear force diagram? You may remember this. We definitely have done it. It actually has no effect. No effect. That is important to understand. So I'm going to use this faint gray lines here to say that nothing happens here really. It's kind of amazing that you have a load case, but it has no effect on the shear force diagram. However, it has a very important impact on the bending moment diagram, and the bending moment diagram actually now has a jump or a drop in it. It is actually the same way that the concentrated force behaves relative to the shear force diagram. We now have a concentrated moment impacting the bending moment diagram. And so what you will find is actually that you have a clockwise or counterclockwise jump. And let's think about what that means. So this is turning counterclockwise, this is turning clockwise. If I now were to cut the system here and I come from the right side, so I release the entire system and bring in my internal force at that location, let's say this M here, so you can see that that would actually put the counterclockwise into balance. So the jump here, due to this force, would make it more positive because they are already acting against each other. However, if I cut the system here and then look at this portion of the system, so I move this purple arrow up to here and then look at only this part, then you see that they actually rotate together. So you would end up with a negative jump here. So symbolically, how that would look like would be with a jump that has the magnitude of the moment. And let's draw this one here. And then we have another one on the other side. But again, we need to understand from where to where we are jumping here. So this is positive. So you actually end up going from here to here. And I will symbolize that in a second. Whereas this one here would be negative. So that means you go from here to here. So I guess the best way to do that is by, for example, saying that, hey, I'm starting here and I'm giving myself an arrow here, and then I jump down, and then maybe I have something else going on here. Whereas on the other side, it's actually the opposite. I have a force that wants to, or a moment that turns it more positive, and therefore I'm going in this direction first, then I'm jumping up, and then I move on in this direction. So in this case, we would be looking at positive here, negative here, negative here. But different scenarios are different, and please don't get hung up on this if that kind of confuses you, like why it's up and down. I think it's enough if you remember that you have a jump in your moment diagram. That's the most important thing to understand here. All right, last but not least, we have the no load case, which you kind of already talked about, because that means that everything is zero there, and we can just draw that we have a shear force that could be zero, it could be positive, it could be negative. So let's just pretend that it's positive here in this case, and maybe just to be on the safe side so nobody sues me for wrong information, I will also draw another beam with the zero case, and then to be on the 100% safe side, I will also draw one with a negative shear force. And so this would look like this and like this. So we could have zero if there's really unloaded, but it could also be negative. Pretty much this is the case where in some of the previous lectures, the way I used to say that is by nothing happens, nothing happens, nothing happens, right? So because nothing happens, nothing happens, nothing happens, it stays constant, either constant positive, constant zero, or constant negative. So that should make sense. Why do I need to tell you this? You may think, that's already included here, but you need to understand that, of course, this has also an impact then on the actual bending moment, which could be, of course, also in three scenarios then in this case. So we could have the zero case, we could have the positive slope, and we could have the negative slope. And let's symbolize that so we can wrap up the information on this page. So I can have the zero case, which if I have zero shear force, you have zero bending as well. That's actually an important thing to understand. But if I have a positive shear force, I have a positive slope. So remember, that is the positive slope. And then for the negative case, I have the negative slope, which could be like this, for example. But this is also positive, this is also positive. And what we really need to understand is that we have a negative slope here and a positive slope. And that therefore shows us how these cases relate to each other, because remember, the very important thing that we learned before is that from the shear force to the moment we really integrate, or we actually took the derivative to arrive at the shear force from the moment. But we also did this for the load case, so we could have done this integration here, or we could have taken the derivative in the other direction. But please keep in mind that when you integrate, so when you move from here to here or from here to here, that you always have to consider integration constants. Here's an example where you have actually integration constants. There are other examples which are beyond the purpose of this class. So just do not use integration blindly. It's always easier to do the derivative approach, but both of them work. But this completes now our table that you can see here on this page. It will give you a tool to understand which load case scenario leads to what shear force scenario and what bending moment scenario. This is all representative and symbolic, so please don't get hung up on the specifics, like for example that there's an inflection from positive to downwards. It could also be positive and then less positive and so on and so forth. But this should give you a good tool to help you when you're in question about a specific jump or behavior in one of your diagrams. So I hope this will help you to complete your homework and to actually analyze the upcoming example problems. So let's use this tool on one of the following pages and apply it to the upcoming problems that include actually evenly distributed load cases and non-evenly distributed load cases. So let's go ahead and start an example problem on the next page. All right, let the fun begin. And you may be surprised how easy the fun will be for this particular problem, which initially looks overwhelming to students in the classroom. At least that's my experience. But hopefully I can decipher the problem for you and show you how quickly this can be done. You have seen this problem before and you have already calculated the support reactions. Let me remind you that it's a symmetric system and therefore we have symmetric support reactions as well. And the support reactions that we calculated were really 2,000 pounds on each side. And hopefully you can verify this, and hopefully you don't even have to go back through your lecture script to really understand this, because we have 2,000 pounds acting on one side downwards and then 2,000 on the other side. And to put that in balance, I have to use 2,000 pounds at RAY and RBY. So now our goal is to draw the internal force diagram for the entire system and include all significant values. So that means I have to understand how the system behaves all the way through. Now, you usually would calculate your support reactions first. You would do that on this page, but we already done that in a previous lecture, so I don't want to waste your time with that. And then you need to understand how to use the information from the load case to draw your diagrams. And it's very unlikely that a beginner would immediately put all the pieces together when they have to apply it for this. So I recommend that you would start making a cut at 1 foot, at 2 foot, 3 foot, 4 foot, 5 foot, 6 foot, and so on and so forth, and just do as many cuts as possible so that you can understand what is happening in the system. Now I will actually limit myself and make cuts only at specific points that are at 4 feet and at 8 feet. So where I want to cut the system is to the left of the support. Maybe I also would cut to the right of the support and then at the center. So let's move on to the next page and do those cuts. But before I do that, I say it again. If I was new to this and I would still go through the educational experience, probably what I would do is I would cut here, I would cut here, I would cut here, and so on and so forth, until I have a solid understanding of what's really happening. But I move on now and do the cut at these 3 locations. All right, so here's the space for my cuts. So I do as many cuts as necessary. I start with my free body diagram for cut x equals to 4, and we do that to the left. So really what I have is the overhang only, and I have an evenly distributed force on top of there that is acting with, I believe, 200 pounds per foot. So 200 pounds per foot here. And I cut the system right here, which means I have to bring in my internal forces. So I have my moment, I have my shear force, and my normal force. And yeah, it looks strange because it's just hanging in air, and you may think, there's no support here, so why can I cut here? But keep in mind that every part of the structure is in equilibrium. So I can now calculate M at 4 to the left. I can calculate V at 4 to the left and N, but I'm going to spare N from now on because it's really equal to 0. So to calculate my V, you can already see what's happening, right? Because my distance here is really equal to 4 feet. I can write out one last time the equation for you. So the sum of the forces in the y direction is equal to 0, upwards positive, and 0 is equal to minus positive defined V4 left minus 200 pounds per foot multiplied by 4 feet. All right, and now I find that my shear force at 4 to the left is really equal to minus 800, right? 800 pounds in this case. And that is important to understand that it's minus, because that means we have to draw it underneath the beam. Now for my moment, I have the sum of the moments about 0.4 to the left is equal to 0, counterclockwise positive, and 0 is equal to positive defined rotational sense plus M4 to the left, and also plus 200 pounds per foot multiplied by 4 feet. And now be careful, because if you look at the units, you have feet and feet crossed out, and that's pound. But we are obviously looking for a moment, and so it needs to be pound foot. So I need to multiply this once again with my lever arm, and that is 4 over 2 feet in this case. So that is the lever arm from here, where the centroid of this cut system is, to here. And therefore, I can now calculate the moment, and M at 4 to the left is really equal to negative 1,600 pound foot. So again, it's important that it's negative. And I want to stress this, that we actually calculated by rotating about this point, which is the first time that we actually calculated internal forces for evenly distributed load cases. And so I did this no different than assuming that this was a cantilever support, right? You learned this before. And so now I have a cantilever support here, which is actually an internal force. And I used the force per distance times the distance multiplied by the lever arm, which of course results from an evenly distributed force that is having a lever arm that is half its distance. And that's where this 4 over 2 is coming from. But now I'm done with that, and I can move on to my free body diagram for the next portion. So now I can do my free body diagram for cut x is equal to 4 on the right. And that does not look very different, but it looks slightly different, because now I have to include my support reaction as well. But first I include the evenly distributed force. which that's still 200, right? But I also have to include the 2,000 pounds now. So 2,000 right here. And that's pounds. And this is pound per foot. And please understand that we cut right here. And therefore I need to bring in my load, my internal loads, my moment, my shear, and my normal force, but that is equal to 0. We don't care about that. Now I can calculate the sum of the forces in the y direction being equal to 0, positive upwards, and 0 is really equal to v4 to the right. And let's include this one here as well. So now minus positive defined v4 to the right minus 200 pounds per foot multiplied by 4 feet and plus 2,000 pounds. And that computes the shear force for V at 4 to the right. And yes, you can already see that it will jump, right? Because now I have to add the 2,000 to it. So I'm going from negative 800 to plus 1,200 pounds. And that now gives me the shear force. You can convince yourself that the moment would not change. So the moment here just increased a little bit the lever arm, and the 2,000 has no additional lever arm to this internal force. Therefore, I can state that M4 to the right is really equal to M4 at the left, and I don't even calculate that. So that's also equal to minus 1,600 pound foot. And it's one thing to calculate the values. You actually need to understand the shape of the diagram, and that's again why I suggest that you make another cut maybe here and here so that you understand how you start from here to get to this point. I of course can take shortcuts because I've solved so many problems before. I've gone through the educational experience that you are currently going through, and that is why I am able to explain that to you and why I can do this fast. You should not fall into this trap of just doing this if you are puzzled, right? If you already have the answer, by all means, you don't need to do more work than necessary. But if you could not draw the diagram based on these numbers right now, I would encourage you to find the internal forces maybe at 2 feet and then maybe at 0 feet so that you can actually build up the diagram yourself. Let me, just for your educational benefit, go ahead and calculate the moment at the center and the shear force at the center. So let me do a cut or the free body diagram for x is equal to 8 feet, right? So that's where we will have the center cut, if you will. And to do that, I have to now include the entire beam with all its load cases on it. So we had 200 here and then the 300 right there. And of course we cannot forget the support reaction. And I probably should also in this sketch include the dimensions so that we're not confused here because it's not really to scale. So let me go ahead and say that this is 4 feet and this is 4 feet. And this was 200 pounds per foot. And this is 300 pounds per foot. And of course we have 2,000 pounds right here as a support reaction. I cut the system right in the middle, so that means I bring in my internal forces and I know that n is equal to 0. But now I can go ahead and calculate my shear force first. So let's go ahead and do that. Let's say that the sum of the forces in the y direction is equal to 0, upwards positive, and 0 is equal to v at 8, I guess, right? So this is v at 8, and then this is m at 8. So plus v at 8, but it's going in the negative direction, so therefore negative, minus 200 pounds per foot multiplied by 4 feet minus 300 pounds per foot, and that also happens to be multiplied by 4 feet, but that is the 4 feet on the right side, so don't confuse those. And then I also need to include the 2,000, so plus 2,000 pounds. And surprise, surprise, v at 8 is actually equal to plus minus 0. All right, this is important to understand, and it comes actually from the fact that the system is symmetric. I will explain that when we actually look at the final diagram. Hopefully this doesn't surprise you too much that it's actually equal to 0. Let's calculate the moment. So the sum of the moments about point 8 is equal to 0, counterclockwise positive. 0 is equal to plus m8, which is also rotating in the positive direction, plus 200 pounds per foot multiplied by 4 feet. And that now needs a lever arm, and keep in mind that we are actually having the centroid of that force right here, so therefore I'm looking at a lever arm of 4 over 2 plus 4 in this case, feet. So that is the lever arm from here to here, because I'm rotating about that point. That means that I now have to include the 300, so plus 300 pounds per foot multiplied by 4 feet multiplied by 4 over 2 feet, because now I cut right through the 300 pounds per foot force, and that has a centroid or a concentrated force or a force resultant right in the middle, and therefore I'm looking at 2 feet distance here. But I cannot forget, of course, my 2,000, which now rotates in the opposite direction, so minus 2,000 pounds multiplied by 4 feet, because again it rotates about my green cut there. And if I do those calculations correctly, I will find actually that my moment at 8 is really equal to plus 800 pound foot. And of course the plus is important, as you will see on the following page. Let me underline my result here, and let's take a look at the final calculations, which, I'll be honest with you, if I had enough practice in this, I actually would not even calculate anything. I would have just go ahead and draw the diagrams, but you see how I arrived at these significant values and how I used equilibrium for the force and the moment to determine the internal forces at these particular cuts. If you can now go ahead and use these few data points to really draw the internal force diagrams properly, more power to you. That's exactly the point you want to reach in this class. But it is my experience in the classroom that these few values do not lead to successful completion of the diagrams. Of course, I will show you now on the next page how you actually draw these diagrams, but please don't be fooled. It's always something different if you have knowledge explained to you than if you create your own knowledge. Why am I saying that? Because you cannot shortcut knowledge, right? You have to go through a learning experience, and there's really nothing wrong with drawing these cuts and solving these values for additional cuts if you are not there yet. That is something you actually need to do. In fact, that's something I had to do over and over and over again to be able to explain this to you. So this doesn't come from nowhere. This has nothing to do with somebody being smarter or anything. It's just people are more trained in certain concepts. And so please do yourself the favor and really train this concept and practice, practice, practice. And if you cannot connect the dots yet, it's very simple. You just make another cut at 2 feet, at 6 feet, at 8 feet, at 10 feet, and so on, until you understand it. Again, there's no shortcut to your own knowledge. And just because somebody explains something to you and you understand it doesn't mean you can apply it. But in this class and in engineering, you will have to apply this all the time. So if you already have enough data to do that, that's good, you reach the goal. But if not, please expose yourself to more of these cuts, because in the future I will now, from now on, start just drawing these diagrams and explain where it comes from. But it shows up as a surprise to some students sometimes, and it's not a surprise because I have done these things that you see here on this page so many times that I can do many of those things in my head by now, and hopefully you will reach that point too. Maybe you're already there. I'm pretty sure you're much smarter than I am, but I encourage you to practice that until you really understand the concept. Otherwise, there's no point in moving on. But I will now explain to you how these diagrams are drawn, and that of course gives you an additional help. But don't confuse following my knowledge with you understanding the concept and applying the concept. All right, enough talk. It's time to draw the diagrams, and to do that I bring down, as always, my indicators here of where something interesting happens. And actually something interesting happened also at the center line, so I bring that down as well. And then I can start drawing my internal force diagrams. Let's get started with the normal force diagram. So that actually happens to be 0 in pounds in this case, so I don't need to waste a lot of time on that. And then let's go ahead and actually indicate that all of this is 0. And yes, I have to do that for every individual region. But now I will draw the shear force diagram. So we have V here in pound. And the values that we calculated were really minus something. What did we calculate? Minus 800, if I'm not mistaken. So minus 800. And then also plus 1,200. So what did I calculate? Oh, I also calculated 0 here. So this was 0. So minus 800, let's pretend that's right here. And then the plus 1,200 is right there. Now the question is, how do I connect the dots? And again, if you don't know that, please calculate more values along the beam. But I know that I have to have 0 at the beginning, so this has to be 0. And I know that I have an evenly distributed force. And it also has to go down, 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 down with 200 per foot. So it actually becomes fairly easy once you internalize that. And that is that I have a linear function here that goes down to minus 800. Then I have a jump of 2,000 up. And then I go down to the 0. And now you may ask yourself, how does the other side look like? And I let you think about this for a second while I complete this. And maybe you can go ahead and do that. I often see a common mistake in the classroom now, that the students actually think, okay, it's a symmetric system, therefore it goes up here and then goes down and then like this. But one thing we need to talk about is that if the system is symmetric, the shear force is actually anti-symmetric. And you can make clear sense of that because at this point I need to continue going down with a slope of 300 pounds per foot, right? Because you went from here to here with 300 per foot down, and this doesn't change here, so I need to continue. And then I'm jumping up by 2,000, and then I go down with 200 per foot here as well. So the way that looks like then, it would be a continuation of that first center slope here. So that would look like that. And therefore I would end up with a value of minus 1,200 here. And then I jump up by 2,000, which means that here I'm looking at plus 800. And then I have to have a parallel line to the first slope, which would look something like this. And what did I mean by the parallel line to the first slope? I will indicate that for you in just a second. And I mean that this line here is actually parallel to that line. And likewise, this line is really parallel to that line, but that is clear from the picture. And now we have all the significant values included, right? We have the 800, 1200, 1200, and 800. And I can now start drawing my moment diagram, my bending moment, which happens to be in pound-foot. And what do I know? I know a few values. I know that I have a negative 1600. So here I had negative 1600. And at the center, I had a plus 800. That makes it a little bit complicated maybe, but I think we can decipher it. Do I need to calculate something else? Probably not, because I know that the moment must be 0 here. And if you do not believe that, you can convince yourself by just making a cut at that location. But I tell you it's 0 right now, and let's just say that we agree on that. And now I also know that I have a slope that increases further down, down, down. And remember, we have a distributed force here which produces the slope. Therefore here we'll look actually at a cubic function. But it's a negative slope this time, right? So let's actually give us some more space here. And let's say that I have minus 1600 right there. And so I have a little bit of slope, a little bit more slope, and more slope, and more slope. And so this here actually is supposed to be parabolic. And now how do I get to the 800, which let's pretend that's right here. Now I need to compare that to this slope here. So I have a 1200 value here, and then in the middle I have 600, and then here I have 0. So that means that I have to draw a tangent here that is 0. Here I have a very steep tangent, and then I have some tangent in the middle. So that means I definitely end up with a belly up, as my students call it in the classroom. And now I have the left side completed. This, of course, here is all negative, which makes perfect sense if you think about it. Why is negative making sense? Because this beam here is clearly frowning, right? It wants to bend down this way. So that means you have tension on the top and compression on the bottom, which is the opposite to what we usually have. So think of this part as a cantilever, and therefore we have negative bending here. And then there comes the inflection point. So there's actually bending that goes on here, and then here there's some inflection in the bended shape, and therefore we end up in the positive region up here. Now the question is, how do we continue our graph? I want you to think about this. How do you continue at this location and at this location? And probably the easiest to start with is right here, because you know it must be 0 there. And then what do? I think the easiest thing is to follow this slope. I'm 0 here, and then I'm getting negative in my slope, right? 0, negative, negative. And then here I have a positive slope, and it goes from a lot positive to less positive. So therefore, it's actually a mirror image of what I already have here. So I just need to image that over or mirror that over and draw my belly shape here to negative 1600. And then I copy the other side, which was a little bit flatter. And that now gives me my entire diagram, which is negative here on the bottom as well, because I have the very same physical behavior on the right side. Everything here is bending downwards. So here the beam is frowning, and it's actually frowning all the way up to here. So this part is frowning or bending downwards. This part is bending negatively or frowning, or the top is in tension. Whereas from here to here, the bottom is in tension and the top is in compression. And so this is really our first problem for which we saw a linear, or sorry, I should say constant load case. So we ended up with a linear shear everywhere in this case. And then we had a parabolic moment. And by the way, I have to indicate which region is parabolic or cubic or linear, I have to write this next to my diagram when I take a test, because I cannot tell by hand the difference between a parabolic and a cubic function. So I always would include that as follows. Like, let's pretend that we have different regions here. Of course, here it's all the same, so I don't have to really do that, but I would state it like this, that from here to here it is parabolic. And that needs to be clarified, otherwise we cannot provide all the points. But also I included all my significant values here in my diagrams. I included the identifier and the units, and therefore I consider this problem completed. It can go fairly fast once you know what you're doing. Don't be surprised, but again, don't fool yourself. Don't just draw these diagrams, because that will not work out well for you in a quiz or in an exam. I've seen that go wrong many times when students just try to draw. And we can talk about those more in the future, what kind of funky shapes I sometimes see. But for now, we completed this problem, and it's time for us to move on from evenly distributed forces to non-evenly distributed forces. But we will do that on the following page in a brand new example. All right, so here we have our next problem, for which we once again are asked to draw the internal force diagrams. So we have to do that and include all the significant values. This now is a system that has a pin on the left side, a roller in the middle, and then an overhang or a cantilever, which is loaded with an evenly distributed force of 4 kilonewton per meter. And then here we have a sloped distributed force, or a linear distributed force, which is non-evenly distributed and is acting from x equals to 0 to x equals to 3 meters. And I don't want to waste your time with support reactions or with even calculating internal forces right now. That's not our goal here anymore. You can practice and practice and practice that. But the one thing I want to point out here is the physics of the system. So if you take a look at that, you can see that we have 4 kilonewton per meter over 3 meters. And here we have exactly half of that acting. So therefore, we immediately know that the support reaction on the left side actually has to pull down, because we have an imbalance that rotates about this point. Think about what would happen if you would remove this support and then have it balanced over this point. Clearly, because you have more load sitting on the right side, it would rotate clockwise about point B. And so I have to balance that. And if you run the numbers, what you would find is that your support reaction at A, again, is going down, but that actually happens to be 4 kilonewton in this case. And therefore, you have to push up with a little bit more than what's actually sitting on top of the structure. And you have to add the 4, the 3 times 4 times 1/2 here, half because we have the triangular distributed force, and then 4 times 3. And what you will find is that actually turns out to be 22 kilonewton. So I have 22 kilonewton. But you can calculate and verify that by the means of the procedures that we showed you in other lectures. So I will now move on to draw the internal force diagrams. I will not even have to do a lot of calculations. I actually do that as I draw the diagram, because the only internal forces that I really have to calculate are at this location, because everything is already clear to me, but you will see that on the next page. So here we have the system with the empty diagrams given to us, and the first thing that I do is I bring down all my important locations, which I now have them all, and I can of course immediately start drawing my normal force diagram, which in this case I'm actually going to put here on the bottom. So I say that this here is the normal force, which happens to be in kilonewton, and that is all equal to 0. And I should of course draw a 0 line through that. So let's do that. And the reason I put it on the bottom in this case is so that now I can better see all my diagrams at once. All right, let's go ahead and start with the shear force diagram here on the top, which is also in kilonewton, and I like to actually develop them at the same time, so I also start immediately with my moment diagram in kilonewton meters. Now, what do I know? I know that all my diagrams always have to start at 0 essentially and end at 0, so I can already say that they are starting here, and the same is true for the moment, and it has to end up at 0 there as well. Now, what else do I know? I know that I have a distributed force that is non-evenly distributed and an evenly distributed force. So that means I know what's going to happen here and I know what's going to happen here. Let's actually indicate that, and let's say that I end up with a parabolic function here, and I will have a linear function in this region. Now remember that my support reactions were given with 4 downwards, 4 kilonewton, and with 22 upwards. So now I'm pretty much done actually. I mean, not done, I have to draw it, but like I have all the information I really need because I can follow my arrows, right? So I have to go down with 4, start from 0. So let's do that. So I'm going to go down here to -4. And now what happens? I have to go parabolically down to some location. Why do I know that I have to go down? Because I follow my arrow. And why is it parabolic? Because my first arrow is short, the next one is a little bit longer, the next one is even longer, and then very long. So from this point here, I go down, 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 further, further, further down. And so you see it must be parabolic because with every step I go to the right, I go more down. I go to the right and I go even more down, and I go to the right and I go a lot down. So therefore it has to be parabolic. Now where that value is, I don't know yet for sure. I will calculate that in a second, but I know that at this point I will actually have a jump. So let's pretend that I have this here, and then I must have a jump that follows my arrow of 22 up. So now the question is, am I less than 22 here? So do I go through 0 or not? And there's 2 ways I can think about this. One way is I can relate it to the moment diagram, because I know that the bending moment must be maximum over this location here because I'm pulling down. I make the beam frown here, and so therefore it has to pull down. But another way to think about this is I can also invert my logic. So usually we start on the left side and then we follow the arrows, right? But here I have to end up at 0, and so that means I have to follow this arrow down, 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 down to end up at 0 here. And what's easier than calculating from 0? Like we have to go from 0 to here with 4 times 3. So all I have to do is really use a linear function there, as I indicated already, and I have to go down from the left to the right so that I can end up with this equation here, or this function. And this value here is really plus 4 times 3, or in other words, plus 12. And so plus 12 then has to be the endpoint of my jump from here, and the jump has to be 22, and therefore I can already connect those dots, and I can say that my value down here is actually -10 now, right? So I have -10 there, and I have to go parabolically to that point. So let's pretend that I can draw this properly so that somehow this is my parabolic function. And granted, I should now fix this right here. So my x was not right there, but I'm not drawing to scale anyways, so therefore that's okay. I now have a jump from -10 all the way up to +12, because together this is 22, and I have my entire area here on the left side in the negative shear force, and on the right side I have the positive shear force. And I know the functions being linear because this is a constant, and parabolic because this is a linear function. So I now have actually completed my shear force diagram. It can be that simple if you know what you're doing and if you have experience with these problems and if you practice a lot. Now, talking about practice, let's look at the next diagram, which is the moment diagram. We have to now understand if we're talking about a positive or a negative here. So along this line, we obviously must have a maximum. So I can now debate with myself, do I have a maximum value here on the top, or do I have a minimum value here? And how would I figure that out? I know that I have to start at 0 and I know that I have to end at 0. And I think the easiest way to think about it is to release this part of the beam, the right side, so that you actually draw the free body diagram. And I'm just going to introduce my cut here. So I just do it here for now, just because we want to be fast in this example and I don't have to steal more of your time. So I now look at the right cut here, at this portion, and therefore I have to put everything within that cut cloud into equilibrium with that moment. And you can see that the moment is turning clockwise and everything in this cut cloud is also turning clockwise. Therefore, this cannot be in balance unless I flip the arrow around. So what does that mean if I flip the arrow around? It means that it's negative. And therefore, I know for sure that this is the right minimum and this maximum does not exist. So let's actually erase that maximum right there. So let's go ahead and get rid of that. And now I can use my knowledge from the previous pages and I can state that because I have a linear function here for the shear force, my moment must be, of course, parabolic, right? Parabolic. And likewise, here I have a parabolic function, and if I integrate that, I end up with a cubic function. So let's write that. And of course, it's difficult to differentiate this drawn by hand, like how much one thing is a cubic function and one thing is a parabolic function. But of course, you get the idea. So we can now draw this area here as being negative. And the last thing that I need to do is really calculate this point here on the bottom, the M min. And I already know that that is a negative value because I, of course, have indicated that and I explained to you already why it's negative. But how negative is it? It's already included on this page because I already have the cut here and I need to find this internal force. So how much is that? So M min is really equal to 4 kilonewton per meter multiplied by 3 meters multiplied by 3 over 2 meters. And this, of course, is negative as we indicated already. And therefore, I know now that my M min is minus 18 kilonewton meters. And that is already the entire problem. And I included all my significant values. So let's take a look at this problem and summarize real quick. Of course, I don't need to talk much about the normal force diagram. That is 0 because we have no horizontal force. But the shear force diagram here was created starting from 0 and ending at 0 here. We knew that we have a linear increasing load case. Therefore, we needed a parabolic function underneath that for the shear force diagram. And for the constant or evenly distributed force, we needed a linear function. Now, how did we get there? I knew that I end up at 0 here and I knew the slope of this linear function. So I used the reverse method going from 0 to 12 by a slope of 4. And then I had a jump down, which was equal to the 22. And I also knew that I had to go down here by 4 because I have a support reaction that's pushing down. And through the parabolic function and this jump here, I knew how to connect those points and I knew that I went through 0 here. Which therefore meant that for the moment diagram, I have a minimum here and not a maximum. I have a minimum. I knew that it must be cubic because if I integrate a parabolic function, I end up with a cubic function. And on the other side, I have a parabolic moment function because I integrated a linear function. The minimum moment that I calculated here with minus 18 was really derived from a cut in which I separated the right side. I could have, of course, done the left side as well. It doesn't really matter. And some students are sometimes hung up about like, why can you cut the right side to the right of the support? How do you know it's the same as on the left side? You would definitely know that from everything we discussed in this class before. So don't get confused about that. I used the cut cloud here And that is definitely a proper method of doing that, but I want to put your attention to the shear force diagram here and to the fact that we integrated from here to here. And what is integration? Integration is really the area under the curve, right? So if I want to find the area under the curve here, what would I find? I would really find 4 times 3, which is equal to 12. So this value here is 12. Please do not get fooled by this minus 10. That's the value down here. So 12 is the height of the triangle, and then the base is 3, right? And how do you calculate a triangle area? You do that by using the height. And then here you have the 3, which is the base. And then you have the 1/2, right? So really this is base, which is the 3, times height, which is the 12, divided by 2 because you're looking at a rectangle that is cut in half exactly along the diagonal. And so, yeah, we do not have negative areas, of course, right? We have a negative 18 here, but the area content under this triangle is really 18, and so it reflects actually the content here. You could also find the area under this curve, and that would also give you 18. Right, so you have a rectangle in here and then a parabolic function on top of that. You could integrate that and you would find that this value here is minus 18, or you would find 18 and then you would understand that it's negative because we're dealing with negative bending. But that explains, I believe, how I arrived at these diagrams and some shortcuts that you can take to really draw these graphs effectively. Don't get me wrong, there are many different shortcuts that you can only learn through practice, but lucky for that, we have actually a lot of homework problems. So I think you can apply this knowledge in your upcoming homework. But before we do that, let's take a look at the summary page for this lecture, and let's then conclude this lesson. So this is what it all comes down to, the takeaways and the parts that may still be questionable to you. Please go ahead and complete these sections. I will move on to the final checkpoint. Let's see what our checkpoints are for today. So of course, first of all, we can now determine the internal force and bending moments for distributed loads. That was the entire purpose of this lecture. I believe you can now apply that. You also know how to find all significant values that are necessary to really completely represent the internal forces. And really what I should highlight here is the completely, right? So you cannot forget any one of those because otherwise the communication between different engineers is not complete, but you know what you need to do, so you can check this off as well. Then we talked about specific load cases, and what I mean by that is, for example, a concentrated load or an evenly distributed load or any other thing that then produce certain characteristic shear force and moment diagrams. So these diagrams really depend on the load case, as you have seen, and therefore you can now relate these to each other. I think that is where we spent a lot of time in this lecture on, and so we can easily check that off. So now you also understand how the shear force diagram relates to the bending diagram, right? So there's a relationship between the shear force diagram and the bending moment diagram, and that is something we discussed at length in this lecture, so I'm sure we comprehend that as well. Ultimately, you were able to use these methods and also to use differential math, if you will, because we effectively integrated and differentiated so that you can determine the internal force diagrams. So you can use really every tool in your arsenal to arrive at these diagrams. So we can check that off as well. So that now completes our final checkpoint and we are ready to move on to the homework. Let's take a look. So this is where the fun starts. We are now drawing internal force diagrams for distributed forces. As you can see, all 6 problems have distributed forces in one way or the other on them. Let's take a look step by step. The first one is a simply supported beam with just one evenly distributed force on that. That is halfway, or a portion of it is loaded and the other portion is empty. And I'm pretty sure you can easily now draw these diagrams. There's not much help that you need from my end to do that. Here it becomes a little bit more interesting. We now have W1 and W2 acting over the entire length. And just one word of caution here. So number one, your W2 of course may be larger than W1. Then you have to draw W2 a little bit higher. But either way, the concept that I'm going to show you now applies. So the way I like to solve these problems is actually by drawing a line through here and then pretty much treat all this with the same type of, in my case here, W2. And then I apply these here on top of it and this here on top of it. Notice that it's a symmetric system, so that tells you a lot. There's many ways to solve this, and of course that's up to you. But again, I prefer to unify it so that I have one continuous load on there and then have a little bit additional load somewhere. But you may use other methods as well. All right, so now we have a beam here that actually carries concentrated forces, which are symmetric by the way, and a distributed force. So please think about what impact they have on your shear force diagram in combination with the distributed force. And then also, of course, on the moment diagram, notice it's symmetric in length as well, or like the beam is symmetric as well, so CAC. And I believe this should be a walk in the park for you now. Of course, practice makes perfect, but I wish you good luck with that problem. Let's take a look at the next one. So here we now add a concentrated moment to the system, which of course you know how to deal with as well. In fact, this problem probably looks very similar to problem A. So there's not much that should challenge you here, except we want you to be exposed to this additional challenge and how it looks in your shear force diagram and in your moment diagram. Therefore, let's move on to the next problem, which now is a cantilever. And yeah, we didn't solve cantilever beams, but of course you can pull the knowledge together from different lectures and from what we talked about before. Here we have an evenly distributed force sitting on top of the cantilever that's supported on the right side. And we also have a horizontal force acting on it. So that should lead to some fun with the normal force diagram. All right, not much more to tell you here. Let's move on to our last problem, which is a cantilever beam that's now supported on the left side. It has a sloped force, which means we have a horizontal and a vertical component. And be cautious here because you're actually pushing up with that force. So that, of course, has a specific impact on your shear force diagram. Then you also have this non-evenly distributed force, which slopes down from W4 here at the very far left to 0 here on the right over a length of B. But I'm sure with everything we talked about in this class, you can easily solve this problem. If not, if any of these problems really causes some trouble or you have a challenging time with these, that is not a problem. In fact, that's why we're doing it. We want to be challenged in our homework and not in our exams or in the real world. But if that is the case, please go ahead and just split up your beam into more cuts. So for example, if this beam here had a length of 10 meters, I would probably make a cut at 2 meters, at 4 meters, 6 meters, 8 meters, and 10 meters, just to give myself enough exposure to these cuts and to connect the dots properly. And of course, the more you do that, the more you will learn throughout the different problems as you go through them. And probably for the last one, you have to do a minimum of cuts at that point. And that is really the point you want to reach. So my advice to you is do as many cuts as you can on the homework so that you learn as much as you can and be super fast in the real world and in your upcoming exams. You will see that every minute you spend right now will pay off a lot later on. But for now, I wish you good luck with your current homework. And I'm pretty sure that if you made it to this point in the class, you have what it takes to solve this. So don't doubt yourself. Just keep practicing. I wish you good luck with that. I will see you in the next lecture. Until then, stay safe.